What's up, Temple Run gamers? Mr. Cully coming at you, and today we're going to be talking about velocity time graphs and specifically taking a velocity time graph and kind of interpreting what it's talking about an object, its motion, and how to make that into a position time graph. So let me spit out my gum. Made it. And let's go ahead and get started. This is a good review for just kind of what we've been doing over the past couple of days. So what is a velocity time graph? It's basically just a graph that shows us what is our velocity at any point in time. So for example, what does that mean? Well, if you look at this graph, on the y-axis, we have our velocity. All right, so velocity, think about as speed with direction. So let's look at time 2, okay? At time 2, at 2 seconds, I want to know what's my velocity. Well, if you look, it corresponds with this point right here. So at time equals 2 seconds, my velocity is 1 meter per second. That's how fast I'm going at that point in time. Well, let's see, what about like 7 seconds? Okay, well, 7 seconds corresponds to this point right here. And at 7 seconds, I'm going at 4 meters per second. So all this graph basically shows us is what our speed or velocity is at any given point in time. And you can see that it fluctuates depending on where we are at time in time. All right. A negative velocity just means we're going backwards. A positive velocity means we're going forwards. Okay. That's all that means. All right. So let's break this down segment by segment because we can kind of see here that at different points we have different velocities. So like between 0 and 3 seconds right here, we have a velocity of 1 meter per second. That's what that means, okay? So let's look at this lake. Well, according to this chart, between 0 and 3 seconds, what's our segment time? Well, how much time has gone by between 0 and 3 seconds? 3 seconds. That's not supposed to trick you, okay? Segment time right here, that just means it's been 3 seconds. What direction are we heading? Well, remember, velocity is either forward or backward. If it's forward, it's positive. If it's backward, it's negative. Well, what's our velocity here? It's above 0. It's 1. So what direction are we heading? We're heading in the positive direction, or we're heading forward. So I just put a plus sign there. That's all that I do. And then what's my velocity? Well, according to this, my velocity is 1 right there. So what's my unit? 1 meter per second. I'm moving at a speed of 1 meter every second. All right, segment displacement. Well, what's displacement? Displacement is how far are you from where you started. All right. Well, the equation for displacement is speed times time. Well, I have my time here and I have my speed or my velocity. So if I multiply those numbers together, I'm going to get my displacement. So what's 3 times 1? Well, that's 3. 3 what? 3 meters. Okay, displacement's a measure of distance and distance is meters. All right, well, let's think about this a different way. If I want to figure out how far I've gone, my displacement over this time, let's think about it this way. I'm going at a speed of 1 meter per second, right? I'm going at a speed of 1 meter per second through this time span. If I'm going at a speed of 1 meter per second for 3 seconds, how can I figure out how far I've gone? Well, if I'm at 1 meter per second for 3 seconds, I've gone 3 meters. All right. It's kind of like saying if you're going at 60 miles an hour on the highway for 2 hours, how far did you go? You went double that. You went 120. Same concept here. You're just kind of thinking about it conceptually. All right. So there's multiple ways you can get that answer. Let's do the next one. Between 3 and 6 seconds. Well, between 3 and 6 seconds, how many seconds have gone by? 3 seconds. Am I heading in the positive or negative direction? Well, my velocity is above the x-axis. It's above 0, so I'm heading in the positive direction. What's my velocity here? Well, it looks like it aligns with 2 meters per second. What's my displacement? Well, if I'm going at a speed of 2 meters per second for 3 seconds, that would be 6 meters. All right. Again, you could just multiply these numbers together to get 6 meters. All right, so that leg is done. Let's look at the next leg. Between 6 and 8 seconds, that is 2 seconds that have gone by. Again, I'm heading in the positive direction because my velocity is above the x-axis. And my velocity says it's 4 meters per second. So if I'm going at 4 meters per second for 2 seconds, how far did I go? 8 meters. All right, 2 times 4 is 8. All right, next leg, between 8 and 9 seconds, That's just 1 second that's gone by. Again, I'm in the positive. My speed here, my velocity is 3 meters per second. And my displacement, well, if I'm going at 3 meters per second for 1 second, I've gone 3 meters. All right, let's do the next leg. Between 9 and 11 seconds, how much time has gone by? 2 seconds. All right, let's look at where this is at. We want to figure out where we're going. All right, well, this is actually on the x-axis. The x-axis is 0. So between second 9 and 11, for those 2 seconds, I'm not moving. My velocity is 0. So what direction am I heading? Well, if you're not moving, you're not really heading in any direction. So I just put none. Okay. You're not heading in any direction. What's your velocity? Well, if you're not moving, your velocity is 0 meters per second. And if you're not moving, what's your displacement? 0, because you didn't go anywhere. All right, so anytime it's 0, there's no direction, there's no velocity, there's no displacement. All right, that's for velocity. All right, and then let's look at this last leg. This is interesting. So between 11 and 15 seconds, 4 seconds have gone by. This time we're below the x-axis, and it corresponds to this. I'm in the negatives now. What does that mean? Anytime you have a negative velocity, you're going backwards. All right, you're going back to where you started. So this time my direction is negative. Negative what? Negative 3 meters per second, according to this graph. Well, if I'm going at negative 3 meters per second for 4 seconds, how far did I go? I went 12 meters. 4 times 3 is 12. But I went negative 12. I went backwards 12. So my displacement is actually negative 12 meters because I went backwards. I had a negative velocity. All right. So what we just did right here was broke this down leg by leg of this graph. I found my displacement for every single one of these legs. Okay. All right. Well, this question says, what is the total distance traveled by this object? Well, distance is different than displacement. Remember, the way I think about distance is if you're a track star, okay, and you're running a 400-meter track, the distance around the track is 400 meters. You ran 400 meters. Your displacement is how far are you from where you started. So if you start and end at the same place on a track, your displacement is going to be 0. All right, even though your distance, you went some sort of distance. Well, if we want to find the total distance traveled by this object, what we're going to do is we're going to add up all of these displacements together, okay? We're going to add up the 3, the 6, the 8, the 3, the 0, and the 12. We're going to make that 12 positive. Why are we going to make that 12 positive? Well, think about it this way. If you went in reverse in your car for 3 miles, did you travel a distance? Yeah, you went 3 miles. You went backwards, but you still went some sort of distance, okay? So we're going to add all these numbers together. So 3 plus 6 plus 8 plus 3 plus 12, okay, equals, let's see, 3 plus 6 is 9, plus 8 is 17, plus 3 is 20, plus 12 equals 32 meters. All right, that's the total distance that this thing went, including the distance it went backwards. What is the total displacement, though? Okay, well, displacement, this is where we got to factor in how far are we from where we started. So think about it this way. We went 3 meters forward, and then another 6 meters forward, and then 8 meters forward, and then 3 meters forward, and then 0 meters forward, and then we went backward 12 meters. You see how we did that? Forward 3, forward 6, forward 8, forward 3, 0, we didn't move anywhere, and then backward 12. So what we got to do to figure out how far we are from where we started is add all these together and subtract by 12. So let's do that. 3 plus 6 plus 8 plus 3 minus 12. And what does that give us? Well, let's think about it. 3 plus 6 is 9, plus 8, 17, plus 3 is 20, minus 12 would be 8 meters. So our total displacement is going to be 8 meters, even though the total distance we went is 32. Okay. So remember, displacement is how far are we from where we started. Distance is what was the total distance of your trip, okay, including you going backwards. All right, so that's breaking down a velocity time graph. Well, let's go ahead and actually graph this. So I'm going to go ahead and carry over the values we just got as far as displacement goes. Here we had 6, here we had 8 meters. This is all from what we just did. 3 meters, 0 meters, and negative 12 meters. All right, if we want to graph this, okay, if we want to graph a position time graph based on our velocity graph, I need to take those numbers I just got. So imagine that we start at the beginning, okay? And for 3 seconds, I'm going at 1 meter per second. All right, so for 3 seconds, I'm going at 1 meter per second. There's a couple ways we could do this. If I'm going at 1 meter for every second for 3 seconds, then what I'm going to do is I'm going to do 1 meter for 1 second. Here I'm going to do another meter for another second, and another meter for another second, because that's my velocity. All right, and then I could just connect these just like that. All right, and then for the next 3 seconds, how fast am I going? 2 meters per second, which means I'm going to go up 2 meters every second. So it's going to be a little bit steeper, a little bit of a steeper line, kind of like that. All right, so that's one way that we could think about doing this, is you could just look at how fast are you going and then kind of adjust the slope of your line accordingly. Well, I'm going to tell you the way that I do it that I think is a little bit easier. All right, we start at 0. After 3 seconds, how far did I go? Well, we found our displacement for that 3 seconds to be 3 meters. So I'm going to go over to 3, and I'm going to go up 3 meters. All right, and plot a point. Boom. Okay. All right, over the next 3 seconds, I went another 6 meters. So I'm going to go up 6, 1, 2, 3, 4, 5, 6, and over 3. Boom. Connect those lines. All right. And then over the next 2 seconds, I went up 8 meters. So 1, 2, 3, 4, 5, 6, 7, 8. Went up 2 meters. So connect those lines. And then over the next second, between 8 and 9, I went 3 meters again. So 1, 2, 3. There we go. All right. And then over the next 2 seconds, between 9 and 11 seconds, I went 0 meters. Well, if I went 0 meters, that means I'm just flatlining here. Okay. I didn't move anywhere. And then for the last 4 seconds, it says I went backwards 12. All right, so what I'm going to do here is I'm actually going to go my position is going to be closer to 0 because I'm going backwards. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and over 4 seconds. So it's going to look like this. Over that 4 seconds, I'm going backwards 12. And I should be at 8. Okay, this should be 8 meters away, and it is. All right. So there's one way to do that. So based on this velocity time graph, you're able to, big word here, extrapolate the position time graph based on that, okay? So the way it looks is, here I went 3 meters, here I went up 6 meters, here I went up 8 meters, here I went up 3 meters, here I went 0 meters, and here I went backward 12 meters, okay? So you can see how those graphs kind of mirror each other. All right, let's do this. Let's do a couple problems from the homework that we had here as well. All right, let's do a couple easy ones. So here what we're doing is we're graphing our displacement over time, which is another name for position over time, okay? And so we could see for every time, doesn't matter if it was 0 seconds, 30 seconds, 60 seconds, our displacement is 30. All right, so if you're plotting this graph, it's going to look like this. Our displacement at any given point in time is always 30. Well, what does that say about the motion of this object? If at any point in time its displacement, its distance away from home is the same, then what we're saying is it's not moving. Its displacement doesn't change, then it's not moving. So if you're not moving, what's your velocity? 0. So over here, we have a velocity time graph, all right? So we want to graph our velocity over time. Well, here we have the positive region, here we have the negative region. I'm not asking you to plot points for you, I'm just asking you to sketch it. If our velocity is 0 for this whole time, then it's just going to be here on the x-axis, because that's where 0 is, 0 meters per second. All right, so if you're motionless, that means your velocity is 0 too. Okay, you're not moving, you have 0 speed in a sense. All right, so that one's pretty easy. Let's do number 2. Okay. Over here, what we have is another thing that we're plotting, and it kind of looks like this. If you're plotting this along, then you're going to see that it looks roughly, and I'm not doing a very good job, I'm not doing this exact, it looks like this. If you connect it, it just looks like a line. All right. All right, so that's our displacement over time. What does that mean about the motion of this object? If we're looking at this graph, what can we say about the motion of this object? Well, after 10 seconds, it went up about 10 meters. And after the next 10 seconds, it went up another 10 meters. And after the next 10 seconds, it went up another 10 meters, roughly, okay? Well, if you're going 10 meters every 10 seconds, what does that say about your speed? It means that your speed is constant. Your speed is constant in this scenario. You have a constant speed or constant velocity. Here's my velocity. There we go. Oh no. Constant velocity. So if you have a constant velocity and it's positive, you're going away from home, what does that look like over here on this graph? Well, if your velocity isn't changing, let's say, for example, it's 5 meters per second and it stays that, then what it's going to look like on this graph is just a flat line, okay? A flat line that's positive because you're going forward. All right, so this graph, this displacement time graph, corresponds to this velocity time graph. You're staying at a constant rate of change of displacement over time, which is velocity, and that is constant there. All right, well, what if your displacement time graph is not constant? What if you're speeding up? Well, that's what this graph looks like, and I'm just going to kind of butcher this. It looks a lot like that. All right, what if it's curved? Well, if it's curved, then that means down here you're going pretty slow, and up here you're going pretty fast. What's that called? That's called accelerating. You're accelerating, you're going from slow to fast. Well, if your velocity is increasing as time goes on, what does that look like over here on this graph? That means that it's going to start slow and get bigger. So it's going to be a diagonal line like that. Think about it. Your velocity starts around 0. That's why it's kind of low here by the x-axis. But over time, your velocity is increasing. So that's why it is diagonal. It's increasing like this. So this graph shows that you're speeding up because you're getting further and further away, faster and faster and faster. All right, and that's how it corresponds to this graph. Let's do a tough one. Graph number 6. So if we're looking at this graph, this one is tricky. Trickiest one that we will do. All right, just like that. And if you connect these dots, kind of looks like a dome. All right, it's curved. Well, let's think about what's happening to our object right here. What's happening? It starts at home, it starts right here, and, well, it's kind of curving, making like a rainbow. Well, if it's curving like this, and the slope is getting flatter and flatter and flatter, what does that mean is happening to its speed? Well, if it's curving like this, from here to about here, it's slowing down, okay? It's moving forward, but it's slowing down. Well, what eventually happens here at the peak? Well, you tell me, what's its slope? What's going on there? It is stopped. Since it's a flat slope at the top, you think about a hill, the top of the hill is flat, it has stopped. And that is where it actually turns around. Because if you look, what happens after this? It starts coming back towards the origin. So it turns around here at the top of the graph. And then what happens? What happens on this right side of the graph? Well, the slope gets steeper and steeper and steeper. It's going closer to home faster and faster and faster. So it's speeding up in the negative direction. Speeding up in the negative direction. So what does that look like? Well, let's do this kind of point by point. At the start of this graph, what could we say about our speed? It is fast and it's positive, okay? I'm moving away. So if it's fast and it's positive, that means I'm starting out somewhere up here. And then in the middle, what does that say about my speed? My speed is 0. My velocity is 0, which means it would be like right there. And then here at the end, what does that say? What am I doing there at that graph? Well, my slope is steep, which means it's fast again, but this time I'm going back towards home, so it's in the negative direction. So it's going to look like that. So really, this graph, and that's a poor line, do a better job than I just did. That should be a straight line, is going from positive, it's slowing down, it stops, turns around, and it's becoming more and more negative. What would this look like in real life? Throwing a ball up in the air. Okay, think about throwing a ball up in the air. If you throw a ball up in the air, okay, what's going to happen to its speed? Well, if you ever thrown a ball in the air, you know that it slows down eventually and then stops and it comes back down toward you. So this is a graph basically of what would happen if you threw a ball in the air. You throw it up, gravity slows it down, and eventually it stops in midair, okay, for a split second, and then accelerates down towards you. So think about it. This is when the ball would leave your hand. Oops. Ball leaves hand. I'm so bad. This is where it's at its peak. It's kind of stopped. And then what would this point be? This is where you catch it, okay? If you think about it, when you catch the ball, it's pretty fast because it's gained all that acceleration from gravity. All that momentum, I should say. Okay? So this is a classic example of a displacement time graph of throwing a ball in the air. Or maybe even think about the top throw dragster. It goes up, slows down, then comes back down. Something like that. All right. So that is what we've been doing in class, is kind of conceptualizing what's going on, what's the motion of an object based on its displacement time graph, and kind of thinking about how does that correlate to a velocity time graph and vice versa. So it's very, very hard to conceptualize this stuff. It really is. So I'm going to post some other resources for you too to kind of help you visualize what's going on. But I at least wanted to work through some problems that you might see on a quiz. And these are very, very similar to what I would put on a quiz. All right. So I understand it's challenging, but try to think about it and kind of go through this video as many times as you can until you start to understand conceptually what's going on here from graph to graph.